Hello friends, today I am going to teach about Sylow's first theorem. So let's begin. First we write the statement of this theorem. Let G be a finite group and small p be a prime integer such that p raised to the power k divides order of the group G, where k is any integer. Then the theorem says that G has a subgroup of order p raised to the power k. Now I provide the proof of this theorem. We will prove this theorem by the induction method on the order of the group G. So first let order of the group is G, because order of the group G is equal to 2, because 2 is the smallest prime integer. We can let it as p raised to the power k. Now we have to prove that G has a subgroup of order p raised to the power k which is equal to 2. We know that G itself is a subgroup of the group G. So trivially here G has a subgroup which is G itself of order p raised to the power k is equal to 2. Now by induction hypothesis we assume that this theorem is true. This theorem is true for all groups of order less than the order of the group G. That means if any prime raised to the power any integer divides the order of any group of order less than the order of group G, then that group has a subgroup of order the prime. And now we will prove that this theorem is true for the group G. That means the order of the group is equal to G. So first we assume pk divides order of H, where H is a proper subgroup of G. Now as order of H is less than the order of group G. So by hypothesis of induction method, H will have a subgroup of order p raised to the power k, and this implies G also will have a subgroup of order p raised to the power k, because H is a proper subgroup of G. So theorem is true here also. Now we will prove for a group which is not a proper subgroup of G. Now we write here the class equation of the group G, which is order of G is equal to order of Z of G, where Z represents the center of the group G, plus summation any element A doesn't belongs to Z of G and G n of A, where n of A represents the normalizer of the element A in the group G, and this box represents the number of distinct right or left coset of the subgroup n of A in G, and where summation runs over the representation of distinct conjugate class. Distinct conjugate classes, and we give it equation number 1. We know that the commutator subgroup of G, which is G, such that n of A is equal to order of G upon order of the subgroup n of A. If we write order of the group G in the left side and these two expression in other side, then we get but as p raised to the power k, that is the order of the group G, doesn't divide the order of the normalizer of the element A, because here we assume that no any proper subgroup of G divides p raised to the power k. So here p raised to the power doesn't divide the order of the subgroup normalizer. But in this equation, p raised to the power k divides this one, and so this side also is divisible by p raised to the power k. But we see that this is not divisible by p raised to the power k, so this must be divisible by p raised to the power k. That is, p raised to the power k must divides the order of the commutator group, this one. This implies p raised to the power k divides summation over the order of group commutator group. This is equation number 2. Now from 1 and 2, from 1 we can see p raised to the power divides this one, and p raised to the power divides this expression. So this must be divisible by p raised to the power k. So from 1 it implies that p raised to the power must divides the order of the center of the group G. This is equation number 3. Now as p raised to the power k divides the order of the center of the group G, this implies p also divides the order of the group center of the group G, because any exponential power of any prime if divides the order of any group G, then the prime raised to the power of 1 must divide the order of the same group. Now by a theorem named Cauchy theorem, Cauchy theorem states that if any prime divides order of a group which is finite, then the group must have a cyclic subgroup of order the same prime. From this expression we can conclude that Z of G, which is center of the group G, must have a cyclic subgroup of order the prime P. Let the center cyclic subgroup is generated by the element X, then the cyclic subgroup X generated by X is equal to E x square x raised to the power 3 x raised to the power 4 dot x raised to the power p minus 1. Here the order of this group is p, where E is the identity element of this cyclic subgroup. Now we know that cyclic subgroup of any group is normal in that group. So this cyclic subgroup generated by X must be a normal subgroup in the group of G. Here also we can consider a quotient subgroup G upon the cyclic subgroup generated by X. Because it is normal, so this becomes a quotient group. Now clearly P raised to the power k minus 1 divides the order of the quotient group, because P raised to the power divides the order of group G, so we can write order of the group G is equal to P raised to the power k into M, where M and P are co-prime, that is M doesn't divide the prime P. Also the order of the cyclic subgroup is P, so P raised to the power k minus 1 must divides P raised to the power k into M upon P raised to the power 1. This implies P raised to the power k minus 1 must divides P raised to the power k minus 1 into M. This is true, but P raised to the power k into M is the order of the group G and P raised to the power 1 is the order of the group cyclic subgroup generated by the element X. So we can imply that P raised to the power k minus 1 must divide the quotient group G upon the cyclic subgroup generated by X. Now from induction hypothesis, the order of this subgroup is less than the order of the group G. So we can conclude by induction that this group has a subgroup of order P raised to the power k minus 1 by induction hypothesis. Let this be the required subgroup of order P raised to the power k minus 1. Now the order of this subgroup is equal to P raised to the power k minus 1. So we can imply the order of P is equal to P raised to the power k minus 1 into the order of the cyclic subgroup generated by X, which is equal to P, and the order of the group P becomes P raised to the power k, and P is a subgroup of G and of order P raised to the power k minus 1. So here we get a subgroup P of G having order p raised to the power k if p raised to the power k divides G. So in all the condition this theorem is true. So Sylow's first theorem is proved. Thank you friends. If you like my videos, then please share it to your friends, and if you didn't subscribe my channel, so then please subscribe my channel. Thank you.